acquired by Twitter in 2019. So, I mean, we are very happy to have you here, Michael, and forgive me if I forgot something which was worth mentioning, but your career is plenty of awards at this point in time. So happy to leave the stage to you, and a virtual applause for your talk. Thank you.
Thanks. Thank you very much. Thank you for the introduction, and thank you for inviting me here. Really great to be here and present. So today I would like to talk about what we call geometric deep learning, and essentially it's probably I will show just part of it, but it's plan or a part of a plan that we try with an entire community that formed around this topic to propose for machine learning and deep learning problems at large. So let me start with the first term in this title, geometry. And for over 2,000 years, this term was exclusively associated with Euclidean geometry, right? We didn't know any other geometry for almost two millennia, but the situation has changed in the 19th century with the introduction of non-Euclidean geometries, works of Lobachevsky, Bolyai, Gauss, Riemann, and many others, have led to the evolution of geometry, and an entire zoo of different geometries evolved, whether it's Euclidean, spherical, hyperbolic, projective, affine, and many of these fields have quickly become siloed and completely disconnected from each other. And mathematicians at that time even questioned which geometry is more general, which geometry is better, and how they relate to each other. So it created a kind of unhealthy situation that luckily was resolved by Felix Klein, that in 1872 he was appointed as professor at a small university in the town of Erlangen in Bavaria. And he was asked to present the prospectus of his research, which he entered the history of mathematics as the Erlangen Program. And there he proposed a quite revolutionary idea that suggested to approach geometry as the study of invariants or symmetries. So essentially quantities that remain preserved under some class of transformations. And the formalism that he proposed for to model these transformations was the language of group theory. So if you think of Euclidean geometry, essentially it's the study of invariants under what is called the isometry group, rigid transformations, rotations, translations, reflections, right? And we know that a lot of structures are preserved by these transformations. They include angles, distances, areas, parallel lines, and so on. If you make this group larger, if you allow affine transformations, they preserve parallel lines, but for example, not areas. And if you go to even larger group, what is called the projective group, then most of the properties are not preserved. And now we can immediately tell which geometry is more general. So he argued that projective geometry is the most general. I should say that his Erlangen program explicitly excluded Riemannian geometry, where you have different local properties, and that took about 50 years more of work, notably the works of Élie Cartan and French geometers, to generalize this approach. But the impact of Erlangen program in mathematics was dramatic, and it also spilled into other fields, notably physics, where this idea that you can use the study of invariance had groundbreaking importance, probably starting with Noether's theorem that proved that in physical systems you can derive conservation laws from fundamental principles of symmetry. And if you think of modern physics, every conservation law has some related invariance. So for example, the conservation of mass or energy is derived from time invariance. And this is, if you think of it conceptually, this is groundbreaking, because all these conservation laws historically were derived by experiments. So you would do an experiment 1,000 times and you measure the energy before and after, and you would say that the energy is preserved. But with Noether's theorem, you could actually derive it mathematically from the assumption that the experiment, if you do it yesterday, today, or tomorrow, will produce the same result, the time invariance. And I would quote here Anderson, who himself was a Nobel laureate in physics, that it is only slightly overstating to say that physics is the study of symmetry. So if we look at machine learning problems, right, and let's look at a simple problem of supervised learning where we have some input, let's say images of cats and dogs, and we apply some black box to want to produce the output that labels these inputs. We can approach these problems as approximation problems, right? So we have some complex function or complicated function that we want to approximate from finite data sample. So this is a very well studied problem. What makes this problem unique and quite unpleasant is that the data is high dimensional, usually extremely high dimensional. And we immediately run into a phenomenon that is called the curse of dimensionality. And well, it has multiple manifestations and multiple ways of presenting itself, but probably the simplest one is the geometric one. So if you think of the simplest classifier that will tell dogs and cats apart, just think of your input space. You take a cat and draw a small ball around it, and you say that everything that falls within this red ball is a cat, right? So if your space is two-dimensional, then the relative volume of this ball or the area of this ball is about 78%. If you go to 3 dimensions, it's already only about 50%. If you go to a 10-dimensional space, it's about 1%. And we can actually analytically express the volume of a unit ball of dimension d. We see that it goes exponentially fast to 0. And in a sense, high-dimensional spaces are vast. So most of the space will be occupied by dogs in this case, rather than by cats. It means that if we were to approximate a continuous function of d dimensions, we'll need exponentially many samples to do it. And for the typical examples of data that we need to deal with thousands or millions of dimensions and reasonable epsilon, the accuracy that we want to achieve, probably these numbers will be humongously large, more than the number of particles in the universe. So this obviously doesn't work, right? And this is the story of machine learning, right? Or the use of assumptions about the problem, what is called an inductive bias, essentially transitioned from the general architecture, such as multi-layer perceptrons that are known to be universal approximators that can approximate any continuous function, to something that has more geometric structure, such as convolutional neural networks that operate on grids and, as we'll see, incorporate translation invariance, geometric priors. But these concepts can be generalized to other structures. So we can talk about generalizations of convolutional neural networks under, for example, rotation invariance using group theory. On graphs, we'll see that the class of invariance we have is invariance under permutations. And on manifolds, this will be what is called gauge invariance, basically invariance under local, the choice of local frame. So maybe somewhat arrogantly, I would like to call this the Erlangen program of deep learning, in a sense that we would like to take the same philosophy of Felix Klein and unify different machine learning architectures, deep learning architectures, from this viewpoint of studying invariance. So the blueprint for geometric deep learning would be, let's start with the domain on which our data lives. So our images, for example, they don't just are not just high-dimensional vectors. They are functions that live on the grid. The structure of the grid introduces a lot of prior, a lot of structure into these vectors, and as a result, the functions that work on them, if they respect this structure, incorporate very strong inductive biases. So that would be our idea. So again, this is the example of the simplest neural network, a perceptron, right? And we know that it can approximate with just 2 layers step functions. So once we can approximate step functions, we can represent step functions, we can approximate any continuous function to any desired accuracy. And that's the universal approximation property. But when we apply it to high-dimensional data, such as images, right, like the digit 3 here, because it considers an image as just high-dimensional vector, it is completely oblivious to the geometric structure, right? So these 2 shifted versions of the same digit will appear as completely different vectors. And as a result, we'll need a lot of data to be shown to the network to learn this invariance from the data. So this is obviously one of the reasons why this simplistic approach didn't work when it was applied in the 70s, and the story of success of what was then called neural networks, now is called deep learning, was initially inspired by research in neuroscience, the classical experience of Hubel and Wiesel, that showed that the connectivity of the neural network and the visual cortex are local. So they implement a form of weight sharing, and the first realization of these ideas was in the neocognitron architectures of Fukushima, and what is now modernly used, convolutional neural networks, the classical work of Jan LeCun, basically made these formal and made this an approach that could also be trained by backpropagation. And that's the battle horse of computer vision and image analysis architectures nowadays. It takes advantage of self-similar structures at different scales, so it implements another geometric prior that is called scale separation in the form of pooling, and the local operations are with shared weights are implemented in the form of convolutional filters. So the number of parameters per filter is fixed in this way, so it doesn't scale linearly with the input size, and the complexity is linear in the input size, so the number of pixels in the image. So let me show you a very different type of input now. So this is a graph representing a molecule. If you are curious, this is a molecule of caffeine. So here every node is an atom, and every edge represents a chemical bond. And this is a very typical type of problems that you encounter, for example, in drug design. So you want to predict, let's say, the binding energy of this molecule to some target, usually a protein. So how would you approach it? You can, of course, represent this molecule just as a vector, as we did in the previous case. But you see now that basically we don't have a canonical way of ordering the nodes of these graphs. So any permutation of these node features will do, right? So we immediately see that we need a different kind of geometric prior. It will be a permutation invariance in this case in order for such methods to work. And molecules are just one example of graph structured data. We encounter graphs practically everywhere. So social networks are probably the most prominent example where we actually need to deal with huge graphs with hundreds of millions or even billions of nodes and multiple billions of edges. Different interaction networks in biology, in medicine, where we have thousands or tens of thousands of different biomolecules, and we represent as a graph the way that they interact with each other. In computer vision and graphics, we use graphs with some more structures, simply shell complexes or meshes, to represent the boundary surfaces of three-dimensional objects, and so on and so forth. So with co-authors, with Joan Bruna, Jan LeCun, Arthur Schlam, and Pierre van der Geinst, we wrote in 2016 this paper that we titled Geometric Deep Learning. I should say that I made up this term in my ERC grant application a year before, and somehow it became used for mainly associated with deep learning on graphs, what is sometimes also called graph representation learning or relational inductive biases. But as I hopefully argued in the beginning, it's a much broader term that tries to approach machine learning problems through the perspective of geometric lens, and graphs are just one manifestation of such geometric priors. So if we compare the more familiar images to graphs, we see that there are several differences. So one notable difference is that in an image, if I take a patch of pixels, right, on which I will be applying some filter like we do in convolutional neural networks, the number of neighbors is always fixed. That comes from the regular structure of the grid, right? On graphs, on the other hand, the number of neighbors can be completely different. And some nodes, let's say the social network, popular users can have millions of followers, and some others, common mortals like myself, maybe a few hundreds or a few thousands. Another probably even more important thing is that the number of the ordering of the neighbors in an image is also fixed. On the grid, I can talk about neighbors to the left or to the right, to the top and to the bottom. On the graph, we usually don't have a canonical ordering of the neighbors. So graph itself, its unique characteristic is that it is unstructured. So we don't have an immediate canonical order of the nodes. And therefore, we will have permutation invariance as opposed to shift invariance in images. So what I will try to discuss today mostly is how to define something similar to convolutional neural networks on graphs, how to do efficiently convolution-like operations, and what actually does it mean to define a convolutional graph. So let me start with this notion, and I guess in this for this audience it will be repetitive, but hopefully it will appear in maybe somewhat different light from it is usually described. So if we look at the convolutional layer, right, as a linear mapping from the input to the output, basically, first of all, we see that it's usually sparsely connected, right? So the ith output is connected to just a few inputs. Usually it's a few pixels around the pixel in an image, and the weights are shared. So I apply the same weight to the input to the left of myself and the right of myself. So if you represent it as a matrix, we see this multi-diagonal structure. And you see that because of the weight sharing, the number of parameters is independent on the size of the input. So this matrix is very special. It is called circulant matrix. It can be obtained by cyclic shifts of a vector that here I denote by W. Okay, so convolution is synonymous with circulant matrices. Now, one thing that we need to see about circulant matrices, unlike general matrix products, the product of circulant matrices is commutative, right? And a particular choice of a circulant matrix is the shift operator. So it is this matrix that shifts cyclically the elements of a vector. And we see immediately that convolution commutes with shift. So this is a property that sometimes is called shift invariance, but the correct term is shift equivariance. So it means that we can first apply the shift and then convolution, or vice versa, the result will be the same. So we also know that commuting matrices are jointly diagonalizable. It means that they will have the same eigenbasis. So I can fix an orthogonal basis and diagonalize in these bases all circulant matrices. And these bases, we can pick up one of the matrices. It's convenient to pick up the shift operator. So the eigenvectors of shift operator happen to be the Fourier basis, the sinusoids, the sines and cosines, or the complex exponentials. And it means that convolution is diagonalized by the Fourier transform. So this there is nothing new about it, I hope. And the last missing piece is that the eigenvalues of a circulant matrix are given by the Fourier transform of the spectral W that forms it. So you see that actually what we obtain here is that the convolution itself emerges from shift equivariance. So we can define actually convolution, we can derive it by saying that I have a linear operation, I want it to be shift equivariant. It immediately follows that it must have this circulant structure because this theorem works in both ways. So basically what we obtain this way is what is called in signal processing the convolution theorem that tells us that there are two ways of computing convolution. We can think of it as a circulant matrix or a kind of sliding window in the spatial domain, or we could compute it as pointwise product in the frequency domain, right? By computing the Fourier transform, and then because the convolution is diagonalized, it becomes element-wise product. So I can multiply by this diagonal matrix of the spectral coefficients of the filter. And so to recap, the convolution in spatial domain is a circulant matrix. We can think of it as local aggregation on adjacent nodes with shared parameters. And this structure comes from the underlying grid structure. And because all circulant matrices are diagonalized by the eigenvectors of shift, the Fourier transform, we can also compute convolution in the frequency domain, right? As I showed in the previous figure. And what is also interesting is that on grids, because the Fourier matrix has redundant structure, we have different fast Fourier transform algorithms that can do this matrix vector product in n log n operations, right? And if the filter is small, we can do it in order of n operations. Now, let's go from grids to graphs. And for a graph, again, we have basically a graph is a collection of nodes that can be numbered from 1 to n. But the key here again is to say that this numbering is completely arbitrary. So the nodes can be permuted in any way we want. And edges are just pairs of nodes. They can be directed or undirected. So let's, for simplicity, assume that they're undirected. We also can talk about neighborhoods. So neighborhood will be just set of nodes that are adjacent, that are connected by edges to a node. And also what we mentioned before, the set of nodes doesn't have a canonical order. So again, it can be defined up to any permutation. And finally, we equip the nodes with some features. It will be d-dimensional features that if we provide some ordering of the nodes, we can put them into a matrix that we can call X. Okay. And well, same way we can define also edge features. Allow me to skip it. So the structure of the graph can be represented by an adjacency matrix that at position ij has a non-zero value if there is an edge from I to j and 0 otherwise. Okay. And obviously you can see that the adjacency matrix for undirected graph is symmetric. Another important construction that is typically seen in graph signal processing and graph learning is what is called the graph Laplacian. So the Laplacian, the best way of thinking of it is measuring how different you are from your neighbors. So what it does, it takes a weighted average of the neighbors and subtracts it from the value of the feature at the node itself. Right, and you can write it in matrix vector notation like this. So A here is the adjacency matrix, D is the diagonal degree matrix. So I should say that Laplacian, well, because it measures how different you are from your neighbors, you can use it as a quadratic form that is called the Dirichlet energy that can quantify how smooth the signal is on the graph. If the Dirichlet energy is 0, it means that it's constant. If it's high, it means that it changes a lot. When I move from a node to a neighbor, the features will change a lot. So Laplacian is really ubiquitous in all fields of mathematical physics. You can define it on different objects, on manifolds, where it's called Laplace Beltrami operator. You can discretize it on meshes. So the cotangent Laplacian is very common in geometry processing and computer graphics. You can even define it on metric spaces. So how do we get from here to defining convolution on graphs? And we've seen that there are two ways of doing convolution on Euclidean domains on grids. One was local aggregation with shared parameters in the spatial domain, circular matrices, and another one was using the Fourier transform. So let me start with this second view, the spectral view, using the graph Fourier transform. So if I look at the graph as a degree, look at the grid as a graph. Basically, this is how the grid with periodic boundary conditions look like, right? So this is what is called the ring graph, and its adjacency matrix looks like this. So you probably immediately recognize the shift operator that we've seen before. So indeed, the adjacency matrix of the ring graph is the shift operator. So we can take the adjacency matrix as a graph of a graph and compute its eigenvectors. That would be the analogy of the Fourier transform, right? So in fact, we can use not only the adjacency matrix, we can use other operators that we can define on the graph. For example, it could be the graph Laplacian. And there are different schools of thought in graph signal processing that either use the adjacency or the graph Laplacian. The two will produce the same eigenvectors on a grid because they're all jointly diagonalizable, but the results will be somewhat different on graphs. But overall, it's more or less the same. For undirected graphs, both of these matrices are symmetric, so we'll have orthogonal eigenvectors. When the matrices are non-symmetric, then it requires more elaborate analysis, but I hope to convince you that we don't really need it. So this is how the Fourier vectors, the basis vectors look like on this ring graph, right? So these are the first eigenvectors of the Laplacian, the classical Fourier basis. And this is some more interesting graph. That's how the first eigenvectors of the graph Laplacian look like. So from here we get an immediate recipe for doing convolution on graphs, right? So in order to compute convolution of X with W, we simply compute the graph Fourier transform, right? Computing the eigenvectors of the adjacency or the Laplacian of the graph, multiplying our vector by this matrix, multiplying by diagonal matrix of the filter coefficients that are designed or learned in the frequency domain, right? So we already designed the Fourier transform of the filter, and then the inverse graph Fourier transform. Okay, so looks exactly the same like we did before. The disappointment comes here in the complexity. So we don't have Fourier transform on graphs. This is a dense matrix by vector multiplication, so it costs order of n squared. And if you were to compute the eigenvectors, so that's an extra cost, that will be typically almost n cube. Usually these matrices are sparse, so you can compute maybe more efficiently, but probably the upper bound is n cube. Same thing for the inverse Fourier transform, right? So if we compare it to the classical case, the Euclidean case, we could apply the filter with worst case complexity of n log n using the FFT, right? And if the filter was small, it would be order of n. Also, the number of parameters in this convolution, these are the spectral coefficients, it's n as opposed to order of 1, right? Then, because we designed the filter in the Fourier domain, we have no guarantee of spatial localization. The filters are isotropic, so they are agnostic to directions. I will talk about it in a second. And what is even worse, that the filters are basis dependent. So if you learn a set of filters on one graph, you cannot apply them immediately to another graph, so they don't generalize. And to visualize it, consider these graphs. So here it's a mesh, so it has some more structure, but the idea is the same. So here we have some signal on this shape, on this graph. I apply a spectral filter to it to do some form of edge detection. So I compute the graph Fourier transform, multiply it by the spectral coefficients of the filter, and compute the inverse Fourier transform. Now, if I perturb the domain, the graph, a little bit, do you expect the result of the filter to be the same? So I will keep the Fourier coefficients. I perturb the domain, the Laplacian will change slightly, the eigenvectors will change a lot, and the result of the filter will be completely different. So it doesn't generalize well. So I mentioned that the filters are isotropic, and this comes from the fact that on the grid we have we can call our neighbors in a specific way. On the graph, on the other hand, the neighbors are given in completely arbitrary order. So as a result, we have permutation invariance or no directions on graphs. And if you think of constructions such as Laplacians, so the Laplacian averages the neighbors. Averaging is an order agnostic operation. Okay. So I should say that the situation on meshes is more optimistic because we do have some ambiguity, but on meshes are locally Euclidean. So once I pick up the first neighbor, I can order all the rest of them in some canonical orientation, for example, clockwise. So we have rotation rather than permutation ambiguity. And as a result, we can do, for example, directed kernels and isotropic kernels on meshes, something that is more challenging on graphs. Okay, so let's have a second look at the convolution. And the second way of looking at it is to consider it as a spectral transfer function. So we can think of it as a function that is applied to our matrix, whether the Laplacian or the adjacency. And if we interpret the eigenvalues of the Laplacian as frequencies, then this P applied to the eigenvalues of the matrix can be thought of as a spectral transfer function, as a filter. And if we parameterize it with a fixed number of parameters, then we get rid of this dependence on the input size, right? And if we can express this function in terms of simple matrix operations, such as powers of our matrix, we don't even need to explicitly compute the diagonalization of the matrix. And it's also possible to guarantee stability under graph perturbations, so to avoid the situations that we've seen before. And it's also possible to guarantee some form of localization, either compact support or exponentially fast decay. Sorry, guys, just a second. Sorry, my son is, has his school. Right. So, so the simplest choice of these filters is a polynomial. So we can take a polynomial of some fixed degree p. It has some fixed number of learnable parameters. So that's order of 1. Then we can efficiently compute it, avoiding the Fourier transform altogether by just multiplying the basically computing the powers of the matrix and multiplying them by the vector to which we apply it. And because the matrix is usually sparse, then this computation will be efficient. It will be typically order of n, or more correctly, the order of the number of edges in the graph. And because Laplacian is local, then the pth power will be localized at p hops of the graph. So basically, the filters will be compactly supported. We can also guarantee generalization. So there are several results of stability under perturbation, and we can also apply it to other operations. The operators doesn't need to be a symmetric matrix. Here, it can be anything. It can be, for example, the adjacency matrix. Okay, so that was the spectral convolution. Let's now look at the spatial convolution. And again, I show you the grid example, the ring graph, whose adjacency matrix looks like the shift operator. So another way of looking at the convolution, we can write this multi-diagonal matrix, the circulant matrix that we had, as a weighted linear combination of the powers of the adjacency matrix, right? Which the zeroth power is the identity matrix, the first power is the shift operator, the second power is shift by 2, right? And so on and so forth. So that corresponds to our intuitive interpretation of convolution, that it's a sum of shifted versions of the signal multiplied by some coefficients, right? So that's exactly the same expression that we've seen before with the polynomial filter. Now, instead of the Laplacian, we use the adjacency matrix, but the idea is exactly the same. And this brings us to probably the simplest realization of convolutional type layers in graph convolutional networks, that are the architecture that is called GCN, or graph convolutional network, where if we arrange the node features of the graph into a matrix, right? So each row here represents the feature vector of a node. We can do two things to these features. We can transform them node-wise. So each vector is transformed independently of others by the same transformation. The simplest case, it's linear transformation, multiplying from the right. And we can diffuse them. So we can multiply from the left by the adjacency or the Laplacian matrix that combines together the features from adjacent nodes. And this is how it looks like. So that's the convolution type operation on graph. We can, of course, concatenate multiple such layers one after another. So if you, for example, you want to have a two-layer GCN that does node-wise classification, that's how it could look like. Okay, so to recap, basically in images, we've seen that we have convolution. In graphs, we have this diffusion or message passing that operates on local one-hop neighborhoods. The number of neighbors is different as opposed to grids, and the ordering of neighbors is not given. So we have permutation invariant rather than shift invariant operations. So let me say a few words about pooling. So the analogy of coarsening of grids can be implemented in different ways in graphs, basically by creating a hierarchy of graphs where we, for example, collapse pairs of nodes and we aggregate features, usually non-linearly, for example, taking maximum. And we can interleave convolutional and pooling layers like in standard convolutional neural networks, with the difference that now we can actually learn the pooling. So we can design a pooling operation that is the optimal for the downstream task. So if we look at this recipe for graph convolution, we see that this is probably the easiest one where we have linear combination of the features of the nodes that is independent of the features themselves. And this is how the early versions of graph convolutional networks worked, such as GCN or similar architectures. We can make it more interesting. We can make still linear combination, but now dependent on the features themselves. So the first architecture of this kind was done by my PhD student, Federico Monti. We call it MONET, or mixture model network. And basically it creates some local system of coordinates that is graph or feature dependent around each node. And in this system of coordinates, we have a set of blobs that act as a kind of soft pixels. So they aggregate information from the neighborhood nodes. And usually they are parameterized as Gaussians, where the parameters of these Gaussians are learnable as well. Somewhat probably more popular and more easier to understand approach is what is called the graph attention network, that can be actually derived as a particular setting of MONET, is when the aggregation is done from neighbors with some learnable attention function. So the weight that I will assign to my neighbor J depends on both features at the node I and at the node J. And finally, we can have a completely non-linear way of aggregating information from the neighbors. And this is the most general message passing neural networks that were introduced by Justin Gilmer in 2017. So in this type of architectures, we have two operations. So we compute the messages from our neighbors that depend in general on the nodes, on the node features, xi and xj, possibly edge features if these are provided, and then we aggregate them. So the aggregation is a permutation invariant function, again, because the nodes have no fixed ordering, and then we update the features of the node I. So one thing to realize is that the choice of the aggregation function is extremely important. So if I look at the aggregation from these neighbors, so the black node is my node I in this figure that I'm trying to update. So you see that if I choose the maximum, for example, it will not be able to distinguish between these structures. So the maximum doesn't care how many times the same feature appears. But the mean, for example, will be able to distinguish between them. On the other hand, if I look at these two structures on the right, so if each node appears twice, then the mean doesn't care, right? But the sum will be able to distinguish between them. So this brings an important and interesting question of how powerful are graph neural networks. And this itself is an interesting question because in case of a fixed domain of grids or Euclidean vectors, we can treat this question as basically from the perspective of approximation theory. So what is the class of functions that our network can represent? Here, because we need to deal with graphs that are different, a convenient formulation would be whether the neural network is able to distinguish between different graphs. And the most natural setting for this is what is called the Graphisomorphism. So we say that two graphs are isomorphic if there is an edge preserving bijection between them. So in other words, the structure of the graph is exactly the same up to ordering of nodes. And it's interesting that this problem, we don't really know its complexity. So we don't have a polynomial time algorithm currently for testing whether two graphs are isomorphic. We also know that it's not NP complete. So it is what is called NP intermediate, or even a separate class of complexity that is called GI complexity, Graphisomorphism complexity. And the classical algorithm from the 60s in graph theory, it was derived by Andrei Lehmann and Boris Weisfeller, that proposed a color refinement algorithm for testing if two graphs are isomorphic. So it's an algorithm that looks at the neighbors of the node and creates a new label for the graph. So initially you start with a graph that is uncolored, and then you look at the sets of the neighbors, or better say the multiset, because the same element can appear multiple times. So here in the first iteration of the algorithm, all the nodes have the same label. So the graph is colored uniformly. And essentially here we have two types of neighborhoods for nodes that have 3 neighbors and nodes that have 2 neighbors. So then we apply an injective function to these multisets, and we obtain a color refinement. So now we distinguish between degree 3 and degree 2 nodes. We can do this process again, and now we have further refinement, right? So we have different colors of neighbors now, so it's different structure. But the next step will not change the color. So at this point we stop and we output the histogram of colors. So if I now take another graph and repeat the same process, and if I obtain a different histogram, I can tell for sure that the graphs are not isomorphic. But if the histograms are the same, I don't know. They are possibly isomorphic. So in other words, it is a necessary but insufficient condition. And in fact, we have examples of graphs which are WL equivalent. So we say that in this case, the WL test fails. And it is interesting that actually very simple structures, such as triangles, cannot be counted by means of the Weisfeller-Lehmann test. So it was shown in 2019 that, I would say actually before, but in the literature on graph neural networks, it was probably first realized at that time, even though I've seen a comment in a blog post by Thomas Kipf already back in 2016 when he makes this analogy, and WL kernels were used for graph classification before deep learning became popular in in the famous paper of Shevardnadze and others in 2010, I think. But bottom line, message passing is equivalent to color refinement. So graph neural networks with the right choice of the aggregation operation are as powerful as WL test. And I should say that there exist high dimensional versions of what is called KWL tests. So essentially it's a hierarchy of tests that work with k-tuples of nodes. And you can design equivalent high dimensional graph neural networks, but they have high complexity. So the best 3WL equivalent GNN has quadratic complexity in space and cubic complexity in time. That was the work of Hagai Maron from Weizmann Institute in Israel. So a different way of approaching this problem is in the form of what we call structural encoding. So if you're familiar with positional encoding that is used in sequence models, you can think of basically assigning a label to each node or each edge that will tell to what kind of structure it belongs. So a kind of indication for the message passing algorithm to maybe aggregate messages or transform messages differently depending on what kind of structure the node belongs to. And this can be done by counting predefined k-size substructures and assigning these counts to each node, and then the message passing just takes this feature vector additionally to the feature vectors of the nodes. In this way, the message passing algorithm has the same linear complexity and local structure. All the complexity is absorbed in this pre-processing step, that if you're unlucky to have a complete graph that is fully connected, then it can be as bad as n to the power k. But in practice, it can be as good as linear if the graph is sparse. And that's most of the cases that we deal with. And we can show that it's strictly more powerful than WL test. And we can always show examples such as strongly regular graphs for which the 3WL test or KWL test in general fails, whereas this method, if we provide the appropriate structures, will be able to distinguish these graphs, right? And here's an example of graphs that fail the 3WL test. In one of them, you have 4 clicks, and another one, you have just triangles. And basically, it means that we create a new hierarchy of algorithms that is unrelated to the WL hierarchy. So, and it allows also to introduce problem-specific inductive biases in your architecture. And we know that in many natural graphs, certain structures are prominent. So in social networks, for example, these tend to be clicks or triangles. In molecular data sets, these turn to be cycles. And if we count these structures, we see that we obtain, in some cases, state-of-the-art performance. Probably it's most striking to see with molecular graphs, where we count structures of size 5 or 6, ring structures of 5 and 6. And these are very prominent structures in organic molecules, for example, aromatic rings. And if you look at the molecule of caffeine, it has example of both 6 and 5 node rings. You see that once we count such structures, the error in predicting properties of these molecules drops dramatically. So in the remaining time, let me try to talk about what are the next steps, in my opinion, that await us in this field. So one thing that is important, and that was really made the breakthrough in computer vision for deep learning, is standardized benchmarks such as ImageNet. And nowadays we have a new suite of benchmarks and different problems in graphs that is called Open Graph Benchmark. Efficiency and scalability that regards both algorithms, software, infrastructure, as well as hardware. If you want to apply graph neural networks at Twitter or Facebook scale, you need to make them be able to work with graphs with hundreds of millions of nodes. Another thing that is typical for social networks, but many other problems as well, is that the graphs that we need to deal with are dynamic. So you cannot think of them as a snapshot, a static thing, but it's actually an asynchronous stream of events that add nodes, delete nodes, add edges, delete edges, update some features, and so on. And this is currently underexplored topic. So at Twitter, we had our first stab at this problem with developing what we call temporal graph networks. Basically a generalization of message passing architectures that are able to deal with this kind of dynamic graphs. interesting results recently using higher order structures. So I mentioned it with structural encoding, but all this field of topological data analysis and computational topology that never really worked in practice because it required a lot of handcrafted features. Now you can integrate these topological losses into deep learning architectures and learn the optimal features in an end-to-end way. So I believe that this and next years we'll see more emerging results from this domain. So finally, we can talk about situations when the graph is not given as input, but it has to be inferred, it has to be learned. And I call this latent graph inference. Some people call it learning the relational structure. So I would like to think of it as a next generation of manifold learning algorithms. Basically, if you think of classical manifold learning algorithms or nonlinear dimensionality reduction algorithms such as isomap or similar methods, basically they came with the assumption that your data, though it's high dimensional, it has low intrinsic dimensionality. You can visualize it as sampled from some manifold that is embedded in this space. And usually the structure of this manifold is captured by a graph, usually k-nearest neighbor graph, that is then embedded or flattened into a low dimensional space. And then you apply some form of machine learning, usually clustering. The problem that these methods never really worked in practice is that all the three steps here were completely separate from each other. So you had to build the graph, right? And the choice of the parameters, for example, the number of neighbors and so on, had a huge influence on how the embedding of this graph looked like, and then as a result, on the output of the machine learning algorithm that you applied in this low dimensional space. So now with graph neural networks, with deep learning pipeline, we have the way of doing all these steps as part of a single architecture that can be trained end to end. So you learn the graph and the filters on the graph at the same time. And they can be made in a way that is optimal for the downstream task. And we've done several works in this direction, for example, for disease classification. Another interesting instance of these methods is what is called algorithmic reasoning, where you can take also this setting where the graph is latent and learnable, for example, a multi-body or multi-particle system, physical system, and you can first train a neural network that, a graph neural network that has generic functions that describe the relations between particles. But then once you learn these generic functions, you infer some symbolic equations that relate them. And basically this way you not only learn the laws of physics, but you also generalize much better. So basically you can learn for example, Newtonian mechanics equations that describe how a system of particles interact. So that was a cool work by Kyle Cranmer and collaborators this year. There are many interesting questions about theoretical understanding, for example, adversarial perturbations and robustness of graph neural networks. There has been done a lot of work in the past year or two on the expressive power, but almost nothing about the generalization capabilities of graph neural networks. So I would say that this is largely an open question. And finally, the most interesting probably are killer apps, so the different applications of graph neural networks. And not in vain, I think this has been one of the most popular topics in machine learning in the past year. And graphs really can describe very abstract systems of relations and interactions at all scales, from nanoscales, such as dealing with molecules, to macro scales, dealing with interactions, interactomes and interaction networks of different biological entities, to entire population networks, social networks, patient networks, and so on. So I myself got to Twitter with a startup company that tried to analyze how lies or misinformation or fake news spreads on social networks. And there is a lot of empirical evidence showing that the way that fake news propagate is different from the way that other news propagate on the social network. So we try to learn with graph neural networks a classifier that would be able to predict whether a story is fake or not from the way that it propagates. And this company was acquired in 2019 by Twitter. So together with a team of my students with whom I co-founded this startup, we were hired by Twitter. And that's where I had the graph learning research. So we are trying to apply these methods to multiple problems, such as recommender systems, which you can also think of as problems in graphs, where you try to encode the graph, for example, the follow network of Twitter users using a node embedding, some graph encoder, and then you can try to predict, for example, whom to follow from the proximity of these node embeddings in the embedding space. It is interesting that in the domain of biological sciences, this was the first year when graph neural networks made a splash, and probably also a unique opportunity to see geometric deep learning to appear on the cover of two major journals in this field. So the Cell and Nature Methods, and the Nature Methods paper, I'm a co-author, so I will tell you a bit more about these works. So the Cell paper dealt with the problem of that is typical in computational chemistry and drug design, which is virtual screening. One of the issues in this field is that the number of molecules that you can potentially synthesize in the lab is huge, something like 10 to the power 60. Whereas the number of molecules you can experimentally work with in the lab or in the clinic is much smaller. So you need to bridge this gap by computational methods, and graph neural networks really excel being fast and accurate. And you can use them for virtual screening, predicting properties of molecules. And Collins at MIT, they found a new class of antibiotics, predicting antibiotic activity of molecules with graph neural network. So they discovered a compound that was originally proposed as anti-diabetic drug that has strong antibiotic properties against even antibiotic-resistant bacteria. That is one of the nightmares of healthcare people, that you will get a bacterium that is resistant to existing antibiotics and is also very contagious. So the COVID pandemic will be peanuts considered in comparison. So our work in Nature Methods, basically we considered how to design proteins from scratch. And proteins are very important. Well, they're probably the most important molecules in our body. All life that we know on Earth is based on proteins, so that's really the molecule of life. And one of the applications, you can use proteins to address targets that are otherwise considered undruggable. And one of the applications in cancer immunotherapy, where you try to design a binder that will block this protein-to-protein interaction in what is called PD-1, PD-L1 complex, program death ligands. So roughly speaking, they tell the immune system not to kill the cell, that it's a healthy cell, and some cancers learned how to express it. So a typical malignant cell will be destroyed by the T cell of the immune system. It allows the tumor to grow and replicate, and then we have a problem and can even die. So by blocking these receptors, we can return the normal function of the immune system, allowing it to kill the malignant cells. And the way that it is done by designing proteins or peptides that will bind to this cancer target. And we can do it with geometric deep learning. So I don't have time to go into details, but that is the method that is described in this paper. So we also look at drug-like molecules in food, considering the way that they bind to the target, basically looking at the protein-to-protein interaction network, and considering the effect of the drug as a signal on this network. And then we can train a classifier that on a set of drugs with known activity, for example, anti-cancer drugs. And this way we have a classifier that tells us whether a molecule has anti-cancer properties or not. And then we can apply it to other molecules, for example, contained in food. And we know that many natural compounds resemble anti-cancer drugs. Actually, many anti-cancer drugs are synthetic analogs of natural compounds that appear in plants. So we can create a map of what we call hyperfoods, food ingredients that are rich with these anti-cancer drug-like compounds. And food is obviously very cool. So we collaborate with a molecular chef that takes these ingredients and try to cook some yummy and nicely looking stuff out of them. So this is just a small piece of the equation because, of course, molecules also interact with each other. So it is interesting to look at their interaction, whether it's side effects or possible synergistic effects. And here as well, graph neural networks can be used. So Marinka Zitnik had a famous paper called Decagon in 2018, where they tried to predict the combinatorial effects of what is called multi-drug therapy. And I'm involved in a collaboration with Mila, where we that is funded by the Gates Foundation, where we are trying to find combinatorial therapies against COVID-19. So probably the vaccine will still allow us to put this pandemic behind, but many people that got sick with this disease still require treatment. So it is important to see if there are drugs that can alleviate these conditions. So to summarize, I focused mostly on graphs. So that was only one piece of these 4 Gs in the Erlangen program of DL. There are many other interesting applications. You can build neural networks that work on manifolds or surfaces. But to conclude, I should say that graphs are very general abstractions. They're useful practically in every field of science and engineering. And we now have a principled way of designing deep learning models that are tailored for these graph structures. It is very cross-disciplinary research. So I myself, by working on these machine learning methods, I've had the luck and privilege to collaborate with people that design proteins, that look for neutrinos on the South Pole Ice Cube Observatory, even cook food and work on molecular gastronomy. So I think it's really cool and very rewarding. So it's very hot field in machine learning. There are several success stories, some indication of industrial applications. So Google recently announced, for example, that they're using it for predicting travel time in Google Maps. But probably most interesting that there are many open questions, and probably it's just the beginning of the tip of the iceberg in this fascinating field. So I will stop at this point. Thank you very much, and we'll be glad to answer any questions if we have time.
Okay, thank you, Michael, for this comprehensive and very nice talk. I'm wondering if we have any questions from the audience.
Hi, can I ask a question, please?
Yep.
Yeah. So first of all, thanks for this excellent talk. Like, it ranged from long done the graph, algebraic graph signal processing by MF Mora and Santarella until now the GNNs. So I would rather put forward this question as a discussion, and I would like to know your views. So as you rightly mentioned that convolution or graph convolution or GFTs, it happens in order of n square, n cube. So what are your views if we avoid convolution and rather we focus on local structures and local operations? For example, learning different local structures like clicks, cycles, triangles, and use a data structure such that it supports parallelism, so that we can reduce the parallel algorithmic complexity, like significantly reduce the complexity, like I would say n log n or log n, for example, which is super less than n square.
Right. So n square. Well, I hope that it was clear, and I apologize that it was not clear. That was basically a motivating example that shows that it's a bad idea actually to use the Fourier transform, basically the eigenvectors of the Laplacian or adjacency, as an analogy of Fourier transform, because it incurs this high complexity. So the message passing, indeed, it is local, it is parallelizable, and it has a low complexity. It has linear complexity, order of n, or in the more general case, order of the number of edges. So I would say that it's a bad idea to use the graph Fourier transform in the form of Laplacian eigenvectors, and it's not used in practice.
Okay.
Yeah. Okay, I think we have time maybe for another question. So if we have any other question from the audience.
Actually, I have one. Hi, Michael. When you go to define the convolution locally, almost invariably all the approaches look at hops rather than at least on graphs, look at hops as a single metric or distance metric to determine the locality. But that's definitely not necessarily always the case. For example, in meshes, you might very well look at actual metric, or anytime you do actually have a metric, you can do that. Have you seen any approach trying to actually define locality in a more general way, not just restricting to hops?
Yeah, very good question. So probably I don't have a short answer because it brings an entire new perspective that we are currently developing. So, and this is basically, you can view graph neural networks as a particular discretization of diffusion equations. So you can think of them as a kind of neural PDEs. So you can do diffusion on graphs, you can do diffusion on manifolds. You can actually think of graphs as samplings from some continuous, maybe higher dimensional manifolds, and graph neural networks and graphs themselves being discretization of these structures. So you can straightforwardly think of time, or which corresponds to the number of layers in this neural ODE or neural PDE formalism, as a continuous parameter. The continuous spatial structure is somewhat more elusive, so that's what we are trying to do now. But you can relate it to the approaches that rewire the graph and decouple the computational graph from the input graph. So basically, think of a continuous diffusion equation, a PDE, that you discretize in different ways, and you derive from it different graph neural network architectures. So that would be probably somewhat related to the notion of locality, because locality in this case will come from some.
Well, you'd have with a PDE or a diffusion, you'd have an exponentially decaying size measure. So,
well, if it's isotropic and homogeneous, probably yes. When you have some anisotropic diffusion equation that has maybe learnable diffusivity tensor, like is done with attention networks, so that might be more complicated.
okay, thank you.
Okay, maybe if I can ask just a bit of a curiosity that I have. So you mentioned this towards the end of the talk, relationship with adversarial robustness and other, I guess, trustworthy aspects of AI and ML. Do you think that with respect to classical feature vector-based representations, when learning on graphs, such properties can be, in some sense, more easily tackled or achieved, or you think the problem is comparable?
So it depends. So it's a very vast field in terms of trustworthy ML. So it's basically it comes probably in the form of some guarantees of performance, right? So with graph neural networks, actually, that was a line of works from Stefan Günnemann from Technical University of Munich. So they showed that you can, in some cases, guarantee performance under adversarial attacks. So adversarial attacks on graphs are much more interesting because they involve both continuous and discrete structures. So you can attack features, and you can also change the connectivity. You can attack a node from multiple attacker nodes. So it's much more varied and richer than the typical examples of attacks, for example, on images in convolutional neural networks. So you can provide some performance guarantees. In general, I think graph theory is rich with a lot of results, certain bounds on performance of certain graph algorithms. So you can relate graph neural networks to these results, then you can obtain some guarantees. I would say that also the problems where you learn the latent graph, you can also consider it as a form of maybe a weak form of interpretability, because the graph itself, it tells you how things are related, and especially if you can express them in symbolic ways, like in the work of Cranmer. So this is very interpretable. Basically, you can learn the laws of physics from just observations of how the system evolves.
Okay, I see. It seems promising then. Okay, if there are no other questions from the audience, I think we can all thank Michael once again, and hoping to see you meet you physically somewhere at some point after the pandemic.
Hope as well.
Okay, thank you then, Andrea. I'm not sure what the schedule is now.
I think this is all for the day. We'll meet again tomorrow morning at 11 for tomorrow's session.
Okay, and thank you everybody.
And thanks again, Michael.